Start in a minute.
Okay. Hi, everybody. This is Nalini Elkins with Industry Network Technology Council, and we have a great webinar today about a very timely topic, which is post-quantum cryptography. Let me start off. So the vision of Industry Network Technology Council, INTC, we're a nonprofit. And what we want to do is give information about the standards activity, and not just at the IETF, but other ones, Broadband Forum, etc., which will impact enterprises and also developers. We have quite a few developers in India, in particular, who are interested in these topics. And to that end, we have a partner, IIESoc, which aims to bridge the gap and increase capacity in India as far as IETF participation. And I certainly hope that we'll be having an IETF in India soon. That would be a lot of fun. Okay, what we have done in the past, we've done IPv6 deployment. We did that for a number of years, and some people have gotten grants from APNIC to do it at universities, and we hope to see more of that soon. We have done security webinars to get you guys trained up in the basics, and now this series is on new work at the IETF. We had Tip Top, which was deep space a while back, and also work on AI. We've received grants from a number of the internet registries, ARIN and APNIC, in particular for IPv6. I'll just say like 3 words about me. I'm a geek and a developer. That's what I do, is I write code for a living. I live to write code. Okay, my life is ill spent. Let's talk about John then. So John is a very well-known cryptographer, and he has a great background, hands-on experience with Ericsson, and he works in applied cryptography, which is development of protocols, but not only protocols, what the attacks that can go on them. So this is a very exciting area, in particular as we move into the quantum era in the next few years. John has worked with many organizations, and we are very, very glad and honored to have him. So John, take it away. It's all yours.
Thank you. Very honored to be here. So yeah, nice presentation. I'm involved in most things Ericsson do with cryptography, research, standardization, product development, and government relations. This will be about PQC, and I will give telecom as an example, but it will not be very telecom specific. I think it will apply to most other industries. And I think all industries need to do this PQC migration as soon as possible. So a little bit about telecom. We are now 4G, 5G, 6G that you all know and use are now truly global standards. That didn't used to be the case. But right now we all take for granted that you can take your mobile phone, travel all over the world, and it works. But this also comes with a lot of complication and requirements. We need really global standards, and you need to take your phone from one country, need to interoperate. We operate with a network from another country. A little bit about the telecom industry. It's highly regulated. Spectrum is given away by the government. Also comes from a monopoly situation where basically all telecom networks were state-owned. Now most of them are privatized, but the state interaction lives on. very standardized, high reliance on standardization. Main organization is 3GPP, but 3GPP use a lot of IETF protocols, heavily reliant on IETF. It's seen as critical infrastructure. We're seeing increased use in industry, but also for mission critical, which is like police, ambulance, and military, which is further increasing the security and privacy requirements. Quite rapid technology evolution, but often it comes in generations. So if you don't get something into 5G, you need to wait sometimes 10 years to get it into 6G. And then there's a lot of evolution that happens in the implementation, of course, that it's not really seen in the standards. A lot of different players in this area. You're probably more familiar with the telecom operators and the smartphone vendors. I work for Ericsson, which make the infrastructure and sell to the operators. So here's a base station and antenna example of what I do, or we do. Here's some history of quantum and security, both very hot topics right now. But when it comes to post-quantum crypto, a lot of these things are very old. Code-based and hash-based crypto, which is now being standardized, were invented in the 70s, basically the same time as RSA and Diffie-Hellman, which is the traditional algorithm we use today. But they were never used because they're not efficient. The move to post-quantum algorithms really started in 2015, when US government announced that they saw this as an urgent threat and would migrate their national security systems to quantum-resistant cryptography. And shortly after that, NIST started a standardization project to standardize new algorithms. NIST is also a US government agency, but all the cryptographers involved come from all over the world. The majority is not from the US. And last year, NIST standardized 3 new post-quantum algorithms. So these are algorithms that are secure, even if somebody builds a very large quantum computer. And this year we have gotten a lot of timelines from governments, at least in the North America and Europe, saying that you should, industry, governments, and everything should migrate as soon as possible. High priority system by 2030 and all systems 2035. And from this year, MLChem, MLDSA, and SLH DSA are mandatory upgrades for all Ericsson products. So what is this threat and how close are we to it? This picture shows in the gray area is where current quantum computers are, all the quantum computers that has been built. And in the upper right, these red lines, that's where you need to be to break current public key crypto. Here exemplified by RSA, but is very similar for elliptic curve cryptography. And this is a logarithmic graph, so the distance is actually quite large, it's several orders of magnitudes. When and if there will be quantum computers able to break RSA, sometimes called a CROC, a quantum cryptographically relevant quantum computer, is very uncertain. Some says 10 years. If you follow Moore's law, like doubling every 2 years, it's 25 years. And if you run out of funding, it may take longer. If you have some breakthrough and you find other uses of quantum, it might be faster. But this is now with the standardization of PQC and government requirements, this is not so important anymore. It's a serious threat and we need to migrate doesn't really matter if it comes in 10 or 20 or 30 years. And they are progressing, but they're progressing quite slowly. But there is at least press releases that they will be able to, like Google and IBM, that they will be able to scale it up in the coming years. But a lot of their earlier marketing material has not been true, so it's very, very hard and uncertain to say what is true in this business. The green area here is where they could be used for quantum chemistry. Here is an example of a government migration timeline, and this is US time. NSA has put out this timeline for US natural security systems, so systems handling top secret US government information. And they have divided a little bit in different use cases, and they say that the first thing you should migrate is software and firmware signing. And the reason is that firmware often stays active in use for a very long time, especially in critical infrastructure. And typically it's very hard or very costly to replace part of the hardware when you already have deployed it. So if you buy new hardware in the coming years, probably not so much PQC hardware out there, but in a few years there will be, think about making them upgradable to PQC. Here are some other countries. India has put out some, I know, some document about Telecom at least and PQC, but no firm timelines as far as I know, but that is probably coming. Indian government is taking this as serious as other governments. So most of these are from this year's, they're very fresh. Top is UK, saying by 2035, high priority, 2035, all nodes, software, hardware in all deployments. European Union says 2030, high priority, and they give software and firmware update as an example, in addition to confidentiality, where you encrypt data so nobody can read it, as to high priority use cases. And they say 2035 for everything. US government is just saying 2035 for everything. And then they also said that use of RSA and elliptic key cryptography, public key algorithms vulnerable to quantum computers, are forbidden, disallowed. France currently recommends PQC everywhere 2030. And these are for deployment. So if you're a standardization organization or you are a vendor selling to others, your products and standards need to include PQC much, much earlier. So if you want to meet these requirements, you absolutely need to start working now, or even better, yesterday. So where are public key cryptography used? Turns out it's used basically everywhere. If you have any modern thing, device, or software, typically it uses a lot of public key cryptography. And typically today it's a mixture of public key cryptography and symmetrical cryptography. Even things that used to be only symmetrical key cryptography now typically is a mixture of public key and symmetrical, because it's the best trade-off. Signatures are used in software and firmware updates. When you send a new firmware software update to a device, it's used for short-term signature for authentication. For example, when you run TLS, the web server authenticates with a signature. If you do digital contracts, you have a signature. Then you have whole PQI systems to be able to handle all these other signatures. And then you have public key encryption. One example of public key encryption is when you connect to a 5G network, your identity is encrypted with a public key. And soon TLS 103 will have a similar functionality where it encrypts the whole client hello sent to the server. And then you use public key encryption, public keys for key exchange, typically today known as ephemeral Diffie-Hellman in TLS, in IPsec, in SSH, in WireGuard. And in the last years, you have seen an explosion of how much cryptography is used. Typically used on several, if you take communication, typically used on several layers in the network stack. And a recent trend has been to push it up in the network stack. And the reason why people have been pushing it up in the network stack, both in standards, in IETF, but also in products, is for mainly two reasons. One is flexibility, so you can do software upgrades without waiting for the operating system, for example. And another is to enable end-to-end encryption. The higher up in the network stack you do encryption, the more likely and likely it is that you can get end-to-end encryption. End-to-end encryption is typically not possible on lower layers. So can you use quantum technologies for security? And that's both yes and no. Mostly no. If you most of the press releases and so on this is just wrong. Quantum key distribution is not mature. Could long term maybe be used as a defense in depth for niche applications. It's a very, very limited technology. It's unauthenticated key exchange on a physical layer. Right now, it also have a lot of security problems. So when you hear ultra secure or something, that's not true. It's practically not secure. And there's a lot of reasons. There's availability problems, not just when you have an attacker trying to hinder you, but also just spontaneously. There are side channels, and at least until a few years ago, everything was hop by hop security. Similar situation with quantum random number generators, they also don't really solve a problem. Problems with current random generators are availability and trust in whoever made them. And quantum random number generators just make these two problems worse. So I would say both of these are basic research. What is very, very useful is quantum sensors for military use. You can do a lot with them. Navigation, finding submarines, finding tunnels, for example. And these things are getting deployed globally now, at least in massive tests, and they will probably be operational in if they are not already very soon. But these things they're expensive and they are heavy, so it typically no industrial use cases. With quantum sensors, you could build excellent radio antennas, but they would be big and bad availability and costly. So it's definitely not something you will see for use in 6G and probably not 7G either, maybe 8G if this is much cheaper. So migrating to PQC is basically you take your product or network or system and you identify all the places you have public key cryptography. And in all these places, you upgrade to post-quantum cryptography, signatures or key exchange. Here's an inventory done for the 5G connectivity system. And all the red rings are places that uses public key cryptography, and all the green places are all the green boxes are places where IETF protocols are used. So you can quite immediately see just from this picture that IETF is very, very important for 3D 5G in general, and extremely important for the PQC migration, because almost all use of public keys in 5G connectivity is based on IETF standards. Unfortunately, there's a tendency quite often, I've seen by governments and people in telecom, to ignore IETF. It's more or less just taken for granted, just like people sometimes treat open source, just something that is there for free. And I think the only so 3GPP and Telecom will mostly wait for IETF to do this work. I'm very active there. Also, one thing that Telecom needs to figure out itself is the IMSI encryption that uses a non-3GPP standard. And there are some other parts, for example, the eSIM provisional is also using public keys and not an IETF standard. Here are other parts of the 5G system. So you have management and you have applications. These are the connectivity layer is very standardized. Management and applications are less standardized. There's some mixture of standardized solutions and proprietary management, and application layer you can typically use whatever you want. So most is not standardized by 3GPP. And then you have the infrastructure layer where typically there's no telecom standardization. Vendors are allowed to implement this, or operators how they want. But typically this also, of course, uses a lot of IETF and NIST and IEEE standards. And what we have identified is that probably the most urgent thing to migrate is the firmware and software update and secure both in the infrastructure layer. Software, like in the connectivity layer, that can easily be updated in a few years. You just download new version of OpenSSL, and by default you have quantum resistant key exchange. So it doesn't need to be harder than that. Just upgrading to the latest version of OpenSSL or OpenSSH and start using that. For key exchange, for signatures in these things, you also need PKI, and that's a little bit more work. Typically, you need hardware security modules and you need to distribute your roots of trust. So that typically takes many years. Here's a little bit about the 3GPP timeline. So 3GPP is the main standardization organization for 5G, also 4G, 3G, and will be for 6G. And 3GPP, you probably all knew about 4G, 5G, and the upcoming 6G. In between these generations, 3GPP work in releases. So release 15 was the first 5G release, and release 21 will be the first 6G specification. And 3GPP as critical infrastructure need to follow these government requirements. At least the operators using 3GPP will have to. So they want to migrate to meet these deadlines. And then the only available options are the NIST algorithms. Right now, I would say they are the only migration options, and also in the future, they will likely definitely be the most relevant and maybe the only practical migration options. IETF is working very hard on integrating now MLChem, MLDSA, and SLH DSA in all protocols. They already have large implementations, and they also have seen already deployments. So right now, 3DPP has begun release 20, and right now 3DPP is doing a PQC study. It's expected that normative work will begin in around a year, so second half of 2026. And this is definitely needed to meet the quite aggressive 2030 deadlines. But in parallel to this, for all the IETF standards, vendors like Ericsson that I work for, we don't really need to wait for 3DPP to do anything. We can start implementing PQC according to IETF specifications in TLS and IPsec and SSH and certificates already now. So I said, in general, government requirements for PQC migration is they are agreeing on the timelines, and now Europe and US are also agreeing quite much on algorithm choices. In the past, before NIST had published final standards, some European countries recommended some other options, but now they all recommend MLChem, MLDSA, and SLH DSA. So I am not aware of any country that publicly do not recommend these three algorithms. However, when you look at the details, there are some differences, which of course make it very problematic for a global company selling products globally. And even worse, if you're in telecom, where you don't need to just selling products globally, you actually products sold to one country needs to be compatible with products sold to all the other countries. You need a single standard. And this can be tricky. Sometimes government doesn't understand this and doesn't see it that way. They want industry to implement their choices and requirements, but that doesn't really work in telecom. So what are the differences? One, maybe the key difference is the view on hybridization. So hybridization means that you take one PQC algorithm and you take one traditional algorithm like RSA or ECC, and you use them both. So you do two key exchanges, and then you derive keys from both of these key exchanges. And in case of signatures, you sign twice, one with the PQC algorithm and one with RSA. And then when you verify both signatures, and fail the signatures if one of them fails. And here we have some European countries saying recommending or requiring hybrids, while US NIST they're fine with everything, and US national security systems and UK saying that they do not recommend hybridization. Then there's some differences in security levels, whether you accept all the security levels from NIST or if you should require something higher like level 3 or 4. In general, I think everything approved by NIST is fine for industry. Most of these government requirements and recommendations come from national security systems, which typically always have had a very high security level, which makes sense, but it doesn't really make sense for general public always. Then another question is whether you should. So MLChem and MLDSA internally now they use SHA-3, so it makes a lot of sense to try to migrate as much as possible to SHA-3 to not have to also implement SHA-2. And then some question marks here are South Korea, China, and to some degree Japan, which have their own competitions or having their own competitions. but it's very unclear at this stage how much these regional algorithms will be used, if they will be used at all, and for industry, or if it's for national security systems. Here are example of the algorithms. So these are the PQC chems. We'll not go into what the chem is. A chem is a key encapsulation mechanism. I think the best way to see a chem is that chem is a specific API. And you can implement both RSA and Diffie-Hellman as a chem, but you cannot use a chem to do some exotic things that you can do with Diffie-Hellman, for example. But for 99% of all use cases, a chem is a drop-in replacement for RSA and elliptic curve Diffie-Hellman. On the top here, you see the current state-of-the-art elliptic curve algorithm called X25519. And as you can see here, you have 32. If you use that in TLS, you have to send 32 bytes to each other back and forth. When you move to MLChem, which provide security against quantum attackers, you suddenly have to send 800 to 1600 bytes, depending on the security level. A good thing with MLChem and lattice-based algorithms are that they're typically very, very fast. So if you have optimized implementation, they're actually even faster than elliptic curve cryptography. So you can typically run this in software, even on a quite slow processor. That's not a problem. But the sizes for TLS and IPsec, that's not a problem. If you have constrained IoT, of course, can be extremely constrained, with like frames being 11 or 51 bytes and so on. Of course, then this is very problematic. But for most use cases, these just work fine. In the bottom, you see some alternative algorithms. HQC will be standardized by NIST. McEllis and FrodoChem will be standardized by ISO. As you see, they are quite much bigger and slower. HQC should be seen as a backup algorithm based on codes instead of lattices. So even if you have some attack on lattices, the expectation is that then codes would be fine, or vice versa. McEllis, Russian government seems to be interested in using McEllis. In general, also have some nice performance for static keys, not for ephemeral keys. FrodoChem is a more conservative version of MLChem, but have very big message fields, and it's very, very slow. So only interest I've seen is this is from some European and Chinese national security systems seems to think this might be a good idea. But I think there's no reason to use this in industry. In general, I think MLChem will completely dominate. And probably in 5-10 years, MLChem will already be used for the majority of things. Here's an overview of signatures instead. A similar situation here, at least for MLDSA. Suddenly the sizes of public keys and signatures are much, much bigger, like 2,000 bytes instead of 64 bytes. Performance is good. And if you have some infrastructure, IPsec and so on, this is not a problem at all. If you look at the web, this works, but you might get some slightly noticeable latency. And the web companies, they care very, very much about not having any noticeable latency. So they would like to see some more optimized alternatives. But I think for telecom infrastructure, this is perfectly fine, and we don't need anything else. SLHDSA is a more conservative option. It's a hash-based option. Some people think that maybe there could be some theoretical attacks on lattices, but I think nobody thinks that there will be any attacks on SLHDSA. You can prove that this is secure as long as the hash function is secure, and we have a lot of experience and knowledge about hash functions. NIST will standardize FNDSA, a smaller signature and so on, but it also uses floating points, which is problematic on constrained devices where you would like smaller signature. Also, might be a security problem and introduce side channels. Almost all attacks on cryptography in the last decades are typically not theoretical attacks. People often think that it's like mathematical theoretical attacks, but typically most of the attacks are implementation bugs or side channels. And in the bottom are NIST after finalizing these 3 or 5 algorithms. NIST started a new standardization project aiming at even more optimized signatures because they noticed that the academic research on these things had advanced and they wanted to get the latest things. So these are the candidates in the current signature options, and as you can see, the signatures are much they're not 2000 bytes, they are a few hundred bytes, which would make a major difference. But these Mayo UOV are built on something called multivariate crypto. SQI sign is based on isogeny based, and Hawk is alternative lattice-based algorithm. In general, it's expected that NIST will standardize one of the multivariate, unless some problems are found. But some people might be able to wait. These will probably not be ready until like 5 years until we see final standards. If you can wait for that and need that, that's good. For telecom, I think we cannot wait for this. We need to deploy MLDSA right now. You might have, in parallel with doing PQC, NIST also introduced new security levels. So you might have heard about 128 and 256-bit security. That works as long as the attack algorithms are perfectly parallelizable, so you can parallelize them over millions of cores or ASIC. But this is not true for some of the quantum attacks, also not true for some of the classical attacks. But so to prepare for this, NIST have, instead of talking about 128, 256-bit security, they're now talking about 5 different quantum secure security categories, and they're all based on symmetrical crypto. So quantum security level 1 is equal to AES 128, and security level 5 is equal to AES 256. And if you have seen press releases or people saying that AES 128 will be broken by quantum computer, it will not. There are some theoretical attacks, but practically it's not affected at all. And this table quite clearly shows that NIST agrees with this view. AES 128 is quantum secure and can continue to be used. Here's some more information about some IETF statements and to ETSI saying that quantum attacks on symmetric crypto is a misconception. 3DPP statement saying that I think this statement from IETF is excellent, and 4G and 5G algorithms will continue to be secure for the foreseeable future. But nonetheless, 60 will probably move to 256-bit algorithms, mostly for other reasons. Another good statement is from the crypto conference Chess last year, when some Jack did calculated how big a quantum computer you would need to break a single AES 128-bit key. And he said you will need a quantum computer covering the surface area of the moon, and that will obviously not happen. You can do similar and come to like millions of quantum computers running for billions of years, or billions of quantum computers running for millions of years. It's not really effective. 6G will probably move to, or very, very likely move to 256-bit algorithms anyway. This was started because partly because some people were worried about quantum attacks, but the current algorithms are a bit old, so there's reason to upgrade them anyway. The new algorithms are much faster in software and hardware, and they have longer and more secure MACs. And when you upgrade to new algorithms, there is not much, there's no problem changing to 256-bit, which also makes them usable for some mission critical applications. So that's what 3GPP will do. The new mode is called GCM SST. So it's a variant of GCM, but which provide better security, better integrity. The confidentiality is the same. 3GPP has also worked on 256-bit authentication and key exchange. And in general, 3GPP believes very much in crypto agility. How you can see all the historical algorithms for 2G, 3G, 4G, 5G. And as you can see, 3GPP always specify more than one algorithm and enforces that both algorithms should be implemented. In that way, if some problem is found with one of the algorithms, could be theoretical or implementation-wise, you can always switch to the backup algorithm. I think that's a good practice in general, if you can afford it. Especially if you have hardware that is hard to update. Otherwise, you can just do a software patch. There's already very large deployments of the NIST algorithms. The final version was published just a year ago, but people think this is really, really urgent. The main largest deployment is key exchange on the web and in SSH maybe. Cloudflare is reporting that 40% of all HTTPS client now use PQC. And if you go to, for example, Ericsson.com, that has already quantum resistant key exchange. And there's also quite a lot of library support. So OpenSSL supports MLChem and MLDSA and TLS, SLH, DSA in certificate. OpenSSL now use MLChem as the default. And early this year, quite a lot of IPsec implementation. I think it was 3 or 4 companies doing press releases basically on the same week saying that they all supported MLChem. Backup algorithms for PQC is a bit problematic at the moment. There's for MLDSA, you can implement SLH DSA for some use cases, but that's much slower and heavier computation. For MLChem, there's currently no good alternative. So right now you have these 3 algorithms. Backup algorithms or maybe more optimized algorithms will come later. What you implement and when is of course very industry or system dependent. For telecom, we will now implement MLChem, MLDSA, and SLH DSA, and then later in maybe 5-10 years we will take decisions whether we will introduce more optimized algorithms or backup algorithms. And that's it. Quite a lot of alignment around the NIST algorithms. I would say globally, these are designed by cryptographers globally. They're definitely not US algorithms. Based on government requirements and some uncertainty, Telecom will probably implement quite high security levels. Uh, just because so we are approved globally. Quantum computers will have no practical effect on AS128. If you have AS128, continue to use that. There is no reason to take any cost to update that, at least not security-wise. Yeah, I think that's it. Any questions?
They're great. Thank you so much, John. Yes, if you have any questions, please put them in the chat window, or raise your hand, and I will recognize you. So here's one question. Yeah, in fact, Mike, let me see if I can have you speak, and then you can just ask your own questions. Hold on for 1 second, and I will figure out how to do that. That will be a trick. Meanwhile, let me ask John one of my questions. I know you had said that China, South Korea, and Japan, I believe, are working on their own stuff. Is it that they're all three together, or is it that each one is working on something?
Yeah, very, very separate things. South Korea had a competition that I think is already finalized last year. China started the competition last year, and in Japan there is some government-driven initiative that might not be a competition. So have nothing to do with each other. It's very hard to know if this is something they do that is as a backup? Do they just want to increase national cryptographic research, or are they actually planning to use this? It's very hard to know. I think in the past, these things have had, at least in Japan, quite limited use. It's not like they are used everywhere. Depends on your country how hard the government can pressure some requirements down on industry and so on. But I think we have to see. But I think none of these are done, and they are typically don't receive very much implementation. So I wouldn't recommend using anything else unless you have to. I don't think they have any big benefits compared to the NIST algorithms.
No, thank you so much. Yeah. So, Mike, why don't you go ahead, and anyone else would please put your questions in the chat window. Thank you, John. Mhm.
Okay, yeah, you have my question in the chat, but the main thing I want to say is, wow, what an amazing presentation, John. Thanks you so much. And Nalini, even kudos to you for getting such a wonderful speaker. My question in the chat was, that this is great information, and I wish I understood more of it than I do, and I'm sure I articulate that on behalf of a lot of enterprises. So we feel like hearing this that we should be doing something either now or in the real near future. Can you give us a few like immediate next steps or things to focus on so we can help ourselves, get prepared for this as it is coming?
Yeah, I think you should. I think having 2035 as a general guide for when you should be quantum secure is probably a good, unless your government says something else, that's probably a good date. And to succeed with that, you probably need to start planning now. So one thing to do is doing an inventory. You check your systems. Where do I have public key cryptography? And then you make sure that that you have a plan for upgrading that system. It might be that the current system will only live for 5 more years, and then I will buy a new one. and then you don't need to think so much more about that system. Then you deprecate it in 5 years, and you focus on making the new system that will replace it quantum secure. But I think you should probably have a high level picture of where you use public key crypto. You might have to pressure your suppliers to implement PQC. Sometimes you might need to do things yourself if you you need to configure things. Sometimes you need to migrate several parts of the system together. You might have two nodes that talk to each other, and then you also need to migrate the PKI and so on. So I think it's a lot of planning.
That makes really good sense. And so, how will this materialize? What I'm envisioning is if we keep our patch levels in the OS up to date and our product levels up to date, it'll kind of magically happen. But that's depending on your vendors. Can we depend on our vendors in those categories?
Probably if you trust your vendors, probably if you use any major software libraries, they will probably be updated. I think hardware might be trickier. I think you need to maybe check with your vendors that they are planning to implement post-quantum firmware update, for example. Probably some vendors are not following these kind of requirements, so they might not be planning and trying to sell you some hardware that cannot be upgraded in 5 years, and that might not be what you want to buy. So I would maybe talk and check with your vendors. If you're a customer, they're probably happy to talk to you and hear what your requirements are, especially if you can point to some government requirements saying this is this is actually a very hard government requirement. Will you be able to help me meet this requirement?
Okay, that makes really good sense. Again, thank you for the great information and the great presentation. Appreciate it.
Yeah, thank you, Mike. So there's so much to talk about. I have so many questions, but John, here's one from the audience. What's the basic difference in the recommendation for SHA-3 versus SHA-2 for PQC? What would you say is the minimum for PQC, 3 or 2?
They are not really, they're quite independent algorithms, so you can use any of them. Um, SHA-3 is a little bit more modern. It has better theoretical security, it's a little bit easier to use. So if you have a choice, use SHA-3. It also, ML-Chem and MLDSA, they require SHA-3 to be used internally in these algorithms. So if you use this algorithm, you will already have SHA-3 accelerator or implementation in some place. So it makes a lot of sense to try to migrate to SHA-3. But if you have SHA-2 acceleration, there's no problem with SHA-2 security if you use that correctly. I think most people, if you do something new, most people, basically everybody agrees that SHA-3 is better. But the only I've seen some government saying that we have a lot of SHA-2 hardware and we want to continue to use that, and that's fine. So it depends a little bit on if you have a lot of legacy SHA-2 implementations or not. But security-wise, both are fine.
No, thank you. So let me get back. And guys, any more questions, please do put them on. Otherwise, I'll go on with mine. So So one of the things I know, for example, Michael, he works for a very large health insurance company, and many of the policy directives that they have come from HIPAA. And then, of course, the banking and credit card industry gets them from PCI. Um, and I can tell you many sad stories about like when PCI deprecated TLS 1.0 and how many people had fines because they were just they I mean easy to say do an inventory or migrate. I mean if you've got like if you've if, like gas stations in outer Mongolia. I mean, seriously, what we got here. So do you have any feeling for PCI, HIPAA, and what's going on over there?
No, I don't have any idea what I would assume that they have started discussing PQC already a while ago. I know a lot of finance banks and so on are discussing PQC and even testing PQC. I think almost all STOs are discussing um, PQC. Different from like if you continue to use TLS 1.0, you definitely have a that had a very practical security problem. PQC is a bit different because it's like we are protecting against some threat that might come in the future. So yeah, but on the other hand, the government requirements and recommendation for PQC is unlike something I worked with crypto for 20 years at Ericsson, and I've never seen any even close to this. I had like talks with many governments globally, including India, and they're all pushing very hard for PQC. So it's a bit different reasons to upgrade. So I think it's hard to say what will happen. But I think definitely all these SDOs are discussing PQC. I'm very sure. Yeah.
That's very interesting. I would be very interested in exactly how one meets said mandate. I mean, what are you supposed to present to say, I'm meeting this, I mean, you see what I'm saying? It's like what's the concrete proposal? Yeah.
Yeah, probably it's just if it's a like PQC mandate, you just need to show that you have MLChem and you have MLDSA and SLH DSA implemented. For most cases, this is typically you read about a lot of high level stuff about PQC migrations, very hyped and so on, but if you look at the tiny details, it's just a boring algorithm update for 99% of the cases. It's not rocket science. You throw out RSA and you put in MLDSA or MLChem. But of course, for an existing system, that is problematic enough. But it's just an algorithm update. So you say I have MLChem and MLDSA and I don't have any RSA and ECC. Yeah.
Yeah, this is a huge discussion because, like, for example, like if you have an MRI machines, I know a lot of them, they have this weird old version of Windows CE embedded. So it's like, seriously, this is what we're doing now. So it's a super interesting problem. But yep, we got our hands, I mean, our work cut out for us. So thank you so much, John. I could talk to you for days. So thank you all so much for coming, and especially John for such a thought-provoking discussion. Our next webinar will be in October, and we'll have Igor Lubashev from Akamai talking to us about CDN issues, and that should also be very interesting. And then in November, we'll have NIST talking to us again about PQC. So stay tuned, and thank you all so much for coming, especially John. Okay. Thank you all. Bye.
Bye.